So last class we did about what we learned from this equation. So as far as the equation is concerned, we see that the equation is E is equals to n phi m omega sine of omega t minus 90 degree. So this basically tells me three information. What are those informations? Those informations are nature of the EMF induced is sinusoidal because this is sine here, and the EMF induced is lagging by the reference to an angle of 90 degree, and the magnitude of EMF will be given by n phi m omega. So basically this equation tells me that the EMF which is induced, this is also a sine form because the reference voltage is sine, so the EMF induced will be also sine. EMF which is induced due to rate of change of flux will lag by 90 degree, and the magnitude of EMF is n phi m omega. Now if we want to find out the magnitude of EMF induced, we always write in VRMS. So whatever magnitude you have got over here, it will be Vm by root 2. So like VRMS, if we find ERMS, it will be EM by root 2. Now if we substitute n phi m omega in place of EM, then if we solve this, we will get that it is 4.44 phi m Fn. So here the EMF which is induced in the primary and as well as in the secondary side, it gives me the equation is 4.44 phi m Fn, where phi m is the magnitude of the flux linking between the primary and the secondary, n is the number of turns, and f is the frequency. So here we have to remember that when we were studying the operating principle of transformer, we have seen that the one thing which remains constant is frequency. So over here, when we get the term of frequency, we should remember that the frequency of the supply voltage and the induced voltage will be same. Now, so one must note over here that it must be noted that induced voltage has term of frequency, so this frequency will be same as a supply frequency. So likewise, now we can write the EMF equation in terms of E1 and E2, where E1 is the primary induced voltage. So when we write primary induced voltage, this N will be replaced by N1, signifying that N1 is the number of turns in the primary side, and when we write E2, we will replace N1 as N2, signifying that N2 is the number of turns in the secondary side. Now, if we calculate the ratio of E1 and E2, we find that it is coming as N1 by N2. Now, N1 by N2 is known as turns ratio in case of a transformer. So, the voltage ratio of a transformer is thus in direct proportion to the number of turns. So E1 by E2 will be equals to N1 by N2. This should be noted. With this formula, we can solve numericals. It is helpful for numericals to solve problems. Now, for an ideal transformer with no internal loss, we can write E1 I1 signifying input power and E2 I2 signifying output power. These two terms can be made equal. So input power is equals to output power. If we write for an ideal transformer, then we will get as E1 by E2 equals to I2 by I1. So once we have got the formula that E1 by E2 is equals to N1 by N2, which is known as turns ratio, but when it comes in terms of current, so it will be inverse ratio. E1 by E2 is equals to I2 by I1. So please note everybody that E1 by E2 is equals to I2 by I1, which is equals to N1 by N2, which is equals to A, turns ratio. So the current ratio of a transformer is thus in inverse proportion to that of the turns ratio. Now, this may be asked as a short question, or many times it is asked that can a transformer work under DC excitation? To answer this question, first I have to keep in mind that when we were learning the operating principle of the transformer, we learned that it is because of electromagnetic induction. So when we say electromagnetic induction means there is a rate of change of flux going on. So the first thing should come in our mind that EMF which is induced is equals to N d phi by dt. Now d phi by dt mathematically signifies what? That EMF induced is proportional to the rate of change of flux. But if we give a DC excitation, or if we give DC supply as the input, then what will happen? For a DC voltage, we will get a constant current. So from a constant current, we will get a constant flux. So for a DC supply voltage, d phi by dt is equals to 0. That means mathematically it signifies that there is no change of flux. D phi by dt, rate of change of flux is 0. So hence EMF induced will be 0. So if EMF induced is 0, so the transformer is not working. But since we are learning engineering, one must try to get an insight of it that what will happen. That it's very easy to say that the transformer will not work because d phi by dt is 0, EMF induced is 0. But what will happen? We must understand one thing, that whenever we give a supply voltage to the transformer, supply voltage is present from the very beginning. Then due to the transformer action, EMF gets induced. So apart from supply voltage, now another two voltage comes into picture, which is induced means the voltage gets generated afterwards the supply voltage is given. So according to Lenge's law, what is the purpose of this induced voltage? According to Lenge's law, it says that it will oppose its own cause. So E1 and E2, since these two are induced voltage in the primary and the secondary side, these two voltages will oppose the supply voltage. So what will happen? So I have written that when no EMF is induced in the primary and secondary coil, there will be no back EMF. Means there is no EMF present in the primary and secondary side to oppose E1 or the supply voltage. So what will happen, since there is no opposition faced by the supply voltage is free to supply a current. Supply voltage is free to supply a huge current in the primary side because there is no opposition faced by the input voltage. So as a result, what will happen? There will be a high current passing through the primary number of turns. So this will increase the current. So what will happen? The insulation present in the winding, it may get burned out of heating. So the total observation is what? Total observation is no EMF will be induced in the primary and in the secondary due to DC voltage application, and there will be a burning smell coming out. So that burning smell is nothing but the burning of the insulation over the windings, since the current is very high now. Now, now to understand the entire operation of transformer, we must understand that how many types of flux are there in a transformer. Now, mainly there are two types of flux. So basically, I have written what, that transformer is a magnetically coupled device. So it means there is no physical conductor present linking, means there is no physical contact between the primary and the secondary side via wire. It is only magnetically coupled. So the entire operation of the transformer means the EMF induced, how much EMF is induced in the primary and the secondary, that totally depends on the magnetically linking means flux due to flux. So mainly over here there are two types of flux. One is called useful flux in the core and another is the leakage flux. So what is the useful flux in the core? Whenever we supply AC voltage, because the voltage is alternating, I have told this a number of times that we have to keep in mind, since the voltage is alternating, the current profile will be also alternating, so as the flux generated will be also alternating in nature. So what happens? This flux means the primary and the secondary coil. So the flux, the major portion of the flux which flows from primary side to the secondary side inside the iron core or a ferromagnetic material core, that is called the useful flux. Now what happens? These windings which are present on the primary and the secondary side, they are very closely placed with each other, and and one copper coil with another copper coil, they are insulated with a double layer of paper. So when we are wounding copper coil on the primary side, what happens? There is a small portion of the flux which links in between the winding. They complete their flux path in between the windings or between its adjacent conductors. So what happens? This flux does not take part in the production of EMF. They are lost. So they are not utilized for the production of flux. So that is why they are known as leakage flux. And the major portion of the flux which transfers from the primary side and to the secondary side, they are known as useful flux. So that is why here I have written that if the input voltage is Vm sin omega t, current will be Im sin omega t. From Im sin omega t, we get phi m sin omega t. Means here it is written to make you understand that the nature of the flux is also sinusoidal. Now what I have written? So the portion of the flux which does not contribute to induced EMF is known as leakage flux, and the major portion of the flux which passes through the iron core inside the iron core is known as useful flux. So the portion of the flux from sin m phi m sin omega t that links with the primary and secondary winding through the iron frame is helpful in the production of EMF in the primary winding and secondary winding, and leakage flux is the minor portion of the flux which successfully link between the they do not link between the primary winding and secondary winding. They complete their part in between their adjacent winding via air gap. Now, what are the disadvantages? So, this leakage flux is an advantage or a disadvantage. So, there are many disadvantages of this leakage flux. So, I have pointed out few of them. So, leakage flux does not link primary and the secondary winding. Hence, they do not take part in the process of energy transfer. Leakage flux draws additional magnetizing current from the input source. This means what? That whenever a current is passing through the means magnetizing current is passing, a flux is generated. So, but to since this flux is a waste state, the amount of current needed to draw this wastage flux is more as compared with that of the utilized flux. Now, higher input current will result in higher copper loss. So, if the input current is more, so copper loss will be more. Leakage flux may link with other metallic parts, and they cause stray magnetic loss, which will reduce efficiency. So, these are some of the points you need to remember for single phase transformer, that the disadvantage of leakage flux. Now, we will go into the construction portion of the transformer. So here I have shown you two figures. One is known as core type of transformer, another is known as shell type of transformer. Now, core type of transformer is what? See, I have drawn the schematic of the core type of transformer where the windings. So here I have shown you the schematic of core type transformer and shell type transformer. Core type transformer is what? Where the windings remain as the exterior part, means winding is wounded over the coil, and for shell type the core remains the exterior part of the transformer. So uh, these are the this is basically the schematic. Now here as far as a construction point of view, we need to understand the difference between core type and shell type of transformer. So here I have noted down some major differences between core type and shell type. Now, it is a request that since we all are studying engineering, don't write this type of difference that you draw one figure. This is code type, this is shell type. There are two limbs in code type, and there are three limbs in shell type. So these type of differences, writing this difference is not encouraged. So since we are studying engineering, we must write some technical points. So some of the technical points I have jotted down. See, the first point I have written what? That in core type transformer, the windings encloses the limb of the transformer, that is windings remain outside. So I have shown you in the schematic the windings which is wounded over the core, they are the exterior part of the transformer, and in shell type the limbs encloses the winding. It means what? In shell type we have three limbs. In shell type we have three limbs. So don't just write the difference that it has three limbs and write like this how I have written. So I've just drawn a schematic. So here you have the winding. Of the shell type. So this is what, sorry.